Welcome to lecture 10 of our system protection course. So in this lecture we'll continue overcurrent protection. In the previous class, in lecture number 9, we discussed how to derive the time of operation, equation for time of operation for a relay, a overcurrent relay, from the torque equation, and it is illustrated using just by demonstration through an electromechanical relay. And then we talked about the definite time overcurrent relay and how it can be implemented in the distribution system. So in this lecture we'll see the implementation of inverse definite minimum time relay, IDMT relay, and also we'll talk about what are the demerits or what are the advantages of directional overcurrent relay. Then we'll little bit talk about directional overcurrent relay, how it can be implemented. Okay, let us start. So we'll see application of inverse definite minimum time relay on a distribution feeder. Let us consider this distribution feeder, which is having a source at one end. This is a single fade, you can say single fade distribution feeder. Okay, we'll also talk about double fade distribution feeder. This is single fade distribution feeder, where at one end we have a source and it is feeding the loads simultaneously connected at different buses. So here we have bus A, bus B and bus C, three buses, and they are connected to loads. And here we have a three-phase distribution feeder, and two relays are connected here. Relay A here, that is at near to bus A, and relay B at bus B. Okay, and the associated circuit breakers connected to relay B and relay A, they are protecting the line section BC and AB respectively as primary protection, and relay A is acting as the backup protection for the section BC, for the section BC. Okay, this BC feeder. So now you can see here that the loads connected here is of 80 ampere maximum load current at bus C, and maximum load current at bus B is 160 ampere, and maximum load current at bus A is 200 ampere. Okay, so let us see. So here the minimum and maximum fault currents at different buses, it is given. At bus C, you can see here at bus C, the minimum fault current is 1000 ampere and maximum fault current is 1500 ampere. And at bus B, the minimum fault current is 2000 ampere and maximum fault current is 3000 ampere. And similarly at bus A, the minimum fault current is 3500 ampere and maximum fault current is 4000 ampere. As we know, the fault location will increase the fault current, the value of fault current will decrease, maximum and minimum fault current values will decrease gradually. Already we have seen, and also we discussed it in the last class, okay, last lecture. So let us see. So the purpose of the relay B, RV, is to provide primary protection to line BC, as I told, and the purpose of relay RA is to provide primary protection to relay to line AB and backup protection to line BC. Okay, and we start the setting process. We'll start the relay setting process from the tail end. This is the thumb rule. From the tail end we'll start. Okay, and what is the way? First we'll decide the CT ratios and clock settings. let us decide the CT ratio and clock setting for both the relays. So at relay B, the maximum load current, assuming 25% overload. So we can calculate this as, so load current is 80 ampere, maximum load current, and we are assuming another 25% overloading. So actually this 80 ampere is not maximum load current, it is rated load current, right? So if we want to calculate the maximum load current, then another 25% is added, so then it will become 100 ampere. Okay, so then assuming 1 ampere relay to be used, let us say 1 ampere relay is being used, then the CT ratio we can choose at the secondary side, we will choose 1 ampere, and the maximum load current is 100 ampere, so we can choose 100:1. Okay, so the plug setting can be done at 100%. So I can say that plug setting I will put at 1 ampere, because plug setting we do it at the secondary side of the CT, so it is at 100% means 1 ampere. Okay, so now let us do the setting, that is finding the CT ratio and the plug setting for relay A. So let us find the maximum load current for relay A, assuming 25% overload. So the load current at bus B is 160 ampere and bus C is 80 ampere. So total load current that will be seen by the relay A will be 160 plus 80, that is around 240 ampere, and 25% overload will assume, so it will be around 300 ampere. Okay, so again assuming 1 ampere relay to be used, the CT ratio can be selected as 300. 300 is the maximum load current, so 300:1. So CT ratio we found 300:1. The plug setting can be done at 100%, that is PH equal to 1 ampere. So 100% means the secondary side current is 1 ampere, so I can write the plug setting 1 ampere. So let us decide the time multiplier setting here. So first of all, we found the CT ratio and then the plug setting. Then in the part B, we will decide the time multiplier setting, which gives the delay. Okay, so time multiplier setting, TMS. Okay, so let us find the TMS. Starting from the most remote relay, that is RB. Okay, so since RB doesn't have to maintain selectivity, because after RB there is no other relay, so it need not to give the backup protection to any other relay, so therefore it doesn't have to maintain selectivity with any other relay, so it can be made to operate fastest. Fastest means it will be operating instantaneously. So fastest is minimum setting, we can set the TMS at the minimum value. Thus the TMS of RB can be set at 0.1. 0.1 is the minimum setting in the TMS dial. It will be clear, very much clear, when you will do your laboratory. In the lab, we will see the electromechanical relays there available in the lab, and you will see that in the minimum setting is 0.1 in those electromechanical relays. Sometimes it is also lesser or higher, but generally it is 0.1. Now to maintain the selectivity between RA and RB, the following constraint must be met. So what is that constraint? This is your constraint. So the operating time of RA for maximum fault at B, okay, so it will be equal to operating time of RB for maximum fault at B. So maximum fault current at B, for which the operating time of RB plus the circuit breaker time, operating time, that is associated with the relay B, and the overshoot time of RA. So that will be the operating time of relay RA for maximum fault current at bus number B. Okay, so let us put the standard curve, a standard inverse definite minimum time equation. So if I write the, already you know the standard characteristics, and already I have shown the standard equations or standard. This is the standard curve for inverse definite minimum time relay. So if I'll substitute TRB, that is operating time for relay B, I can just write the equation 0.14 into TMS divided by PSM to the power 0.02 minus 1. This is the standard equation, IS equation. Now, if I know TMS is 0.1 for RB, and PSM I need to find. So how I will find PSM? If I know the maximum, I know the maximum fault current. Using the maximum fault current, I can find the PSM. So your maximum fault current is at bus B is 3000 ampere. So therefore, your relay will see it as 30 ampere. Okay, just by dividing the CT ratio, that will get, that is 1000 is, sorry, 100 is to 1. So just by dividing it, will get 30 by 1. So it will, the PSM will be 30. Okay, so your plug setting multiplier, okay, your plug setting multiplier will be 30 for the maximum fault. Okay, so then I will substitute this PSM here in this equation, right? After substituting, I will get the operating time for relay B for the maximum fault current at bus location B. Okay, now after finding TRB, now I'll find TRB. Just by substituting this, I'll find TRB here. TRB, we found it as 0.2. Just substituting PSM and TMS, I will find the operating time of relay B for the maximum fault current at bus B. So that is around 0.2 seconds. Okay. Now the operating time for circuit breaker B, that is associated with relay B, is 0.5 second. Now I can find the total operation time will be TRB plus TCB B, that is 0.7 second, 0.5 second plus 0.2 second. So now if I'll find the operating time for relay A for the fault current at maximum fault current at bus B, then I can just add these values. 0.2 plus 0.5, they are nothing but they are the relay operating time at bus B, and the circuit breaker operation time, that is 0.7, and 0.07 is the 10%, that is, we call it the overshoot time for relay A. So now 10% of 0.7, that will be 0.07. So that is the overshoot time for relay A. Okay, so that will give us the overshoot time for relay A, and that is equal to total equal to 0.77 second, which is nothing but the operating time for relay A for the maximum fault current at bus B. Okay, now for relay A, if we'll substitute the operation time, that is 0.77 with the standard equation, after substituting, I'll find also I need to find the TMS setting from this equation by substituting the PSM value. So how I will find the PSM value? Just by taking, so PSM will be here I relay by PS, that is clock setting. So clock setting is, so your turns ratio is around, clock setting is 1 and your turns ratio is 300. Just by dividing it we'll get 10 as clock setting multiplier, and just substituting this value 10 here at this point, 10 at here in the clock setting value, clock setting multiplier, I'll find this. So I'll find TMS equal to 0.26. So this is the setting, TMS setting for relay A for the maximum fault current at bus B. So now our setting is ready for relay B and relay A. Now this is for your relay B, RB and RA. This is CT ratio, clock setting and TMS. So we found the CT ratio for relay B is 100:1 and for relay A it is 300:1. Okay, and similarly for clock setting we have taken 1 ampere for both the relays, and we found TMS for relay B as 0.1, that is the instantaneous setting, that is the minimum setting we say, right? And for relay A it is found 0.26. Okay, now this is your result. Now let us check whether the selectivity for minimum fault current is maintained with this setting. So this is the setting we found for, this is the plug setting and TMS setting for both the relays. Now let us check whether these settings are really suitable for the minimum fault current as well. If it is not, then we need to change, right? So let us check. So let us find the operating time TRB for the minimum fault current. So your, what is the minimum fault current? Minimum fault current is 2000 ampere at bus B. So we'll find just by substituting the PSM. So your PSM will be 20. So just substituting this in the standard equation, I will find the operating time for relay B is 0.22 second, 0.226 second. So expected operating time of RA for this fault should be greater than the total operating time. We can see, calculate here. So your circuit breaker operating time is 0.5 and relay operating time for relay B is 0.226 second. Now both will be added and your overshoot time is 0.1 into 0.226 plus zero point 0.5, that is total is equal to 0.7986, that is equal to around 0.8 second. So your expected operating time of relay RA for this fault, for this minimum fault current at bus B should be greater than this 0.8 second, right? Let us check it. So if it is greater than 0.8 second, then our setting is fine, then we'll go with this setting, right? Let us check it for, then let us just substitute. So in order to find the operating time at relay A for the minimum fault current at B, at bus B, so that will be equal to 0.14 into 0.26. 0.26 is your setting here for relay A, right? 0.26 is your TMS setting. Now your PSM will be, it can be calculated, it will, how it will be calculated, your minimum fault current is 2000 ampere, so 2000 by 300. Okay, so it will be around 2000 ampere by 300, it will be around 6.66. this is your PSM. Okay, so this is nothing but this is the CT ratio, and this is the minimum fault current is 2000 ampere divided by the CT ratio, that is 300:1. So we'll get the PSM as 6.66. Just by substituting we'll get the operating time for relay A as 0.94 second, right? So this 0.94 second is greater than, in fact, 0.8 second, and it is, in fact, it will work, right? Okay, so it should not be less than this value 0.8 second, it should be greater, always greater than or equal to 0.8 second. So Therefore, we found that it is greater than 0.8 second, and now our settings are okay. So we can go with these settings. These are the two settings for relay A and relay B. We can go with these settings for this kind of arrangement for a single end feeder, single end distribution feeder. Okay, so it is greater than 0.8 second. Okay, now we can see here. Okay, now let us generalize this setting, how we'll find the setting for relays for a radial distribution system which is fed from one end only. Okay, single ended radial distribution feeder. Okay, so if this kind of feeder is given, so first we need to find the plug setting of the tail end relay, then we'll go gradually in this way from this side, gradually we'll go towards the source. Okay, so therefore first we'll start with the tail end relay setting, then we'll gradually move towards the source. So let us first think about okay, let us first generalize it. Let us first take the clock setting of RB, and it should be such that IF minimum C greater than equal to clock setting of RB greater than ILC plus overload. Okay, so that means your clock setting can be ILC plus overload or IF minimum C. It should be within this range. Okay. So in the previous example, we took it as ILC plus overload, right? Then we'll do the TMS setting for RB, and that can be set at the smallest value because it is the tail end relay, so it need to be instantaneously operate. So it will be operate at 0.1 second. Then clock setting of RA should be set. So it will be also set as IF min C greater than clock setting of RA greater than, that is, the load current at bus B plus load current at bus C will be added plus overload. Right. Then accordingly in the previous example also we set at ILB plus ILC plus overload. Overload we took as 0.25 into the normal load current, that is around 25% of the overload. So, TMS of RA should be such that the operating time of RA, first we need to find the operating time, then from the operating time of RA we'll calculate the TMS of RA. So operating time of RA for IF max B, that is the maximum fault current at bus B, will be equal to operating time at bus operating time of relay B for the maximum fault current at bus B plus circuit breaker operating time that is associated with relay B plus the overshoot time of relay A. Generally overshoot time is taken as 10% of the 10% of the total operating time of relay B and circuit breaker B. Circuit breaker BRB. Okay. So generally it is taken as 10%. Okay. So guidelines for setting pickup current for relays. So first what we do, pickup current should be above the maximum load current, right? So it should be above the maximum load current. Okay. And pickup current should be below the minimum fault current. Then your pickup current should also be below the minimum fault current of the feeder that has to be backup. Okay. Then the backup relay also should provide time for primary relay to operate. This time interval is known as the coordination time interval. Already we know this coordination time interval, or we call it standard time interval, right? STI sometime, right? So this is already taken. so so these things already we have seen in your example, last example, and we generalized how we can set the clock setting and the TMS in the relay. Okay, so now we'll see the choice between the IDMT and DTOC relay. So in the last lecture we talked about the DTOC, that is definite time over current relay, and in this lecture we talked about the inverse definite minimum time relay. So out of these, what we should choose and how we'll choose. Okay, so this is a feeder, single-ended feeder, which is being supplied at one end with a source impedance ZS and line impedance ZL. Okay, so now how we'll choose which kind of uh, relay we choose, right? Whether IDMT or DTOC. Okay, so obviously IDMT is costlier than DTOC, so accordingly we should choose in order to reduce the cost. So if your line length is short line length, for short line length, that is when your ZS is greater than ZL, right? Your ZS is greater than ZL, that means very much greater than ZL. At that time we can easily choose DTOC, that is definite time over current relay. Why it is so? Because if we'll see the characteristic here, you can see here the characteristic. Uh, the characteristic is plotted here, the fault current versus the fault location. In fact, for a short line, the fault current remains same at the level of E by ZS approximately, right? And for a long line where the ZS is very much less than ZL, at that time it varies, it reduces gradually. Okay, so when it is remaining constant, okay, when the fault current is remaining constant in the line throughout the length, then we can choose the DTOC, definite time over current relay. At any bus we can put DTOC. So if your current is varying with the line length, then we should choose the IDMT relay. Okay, so here we can see, because we know the fault current is E by ZS plus ZL. So when your ZS is very much greater than ZL, then it will remain constant for the short line. Okay, and it will gradually reduce, exponentially reduce when it is a long line where is uh, ZS is less than, very much less than ZL. Okay, so that will reduce the, that will gradually reduce based on the fault location, the fault current, right? Okay, so therefore it is a practice to recommend DTOC relay when your ZS by ZL is, this is a thumb rule, ZS by ZL is greater than equal to 2. So when this is applicable, we can choose DTOC in protection of single-ended distribution system, distribution feeder. So now we'll see the faults are classified into two types, that is phase fault, which don't involve ground, and earth fault, which involve ground, right? So if we'll see the phase faults will be, what are the phase faults? We can see the phase fault will be three-phase fault, that is line to line to line fault, right? Then double line fault, which doesn't involve ground, right? They are the phase faults. And which are the ground faults? All other remaining 9 faults are ground faults, right? Okay, so now you can see here a typical arrangement for three-phase feeder protection. Generally the relay, with whatever relay available or manufactured, it has three-phase protection system schemes, right? It has three phases to be connected, right? These are called phase relays, and also sometime it has earth fault relay also, right? So we'll talk about it in more details. So when there is earth fault, uh, the current flows through this ground wire, which is kind of neutral to neutral wire, right? And in fact that will give us the that will give us, if some overcurrent relay is here, then your relay will trip, give the trip command to the circuit breaker. Okay, let us see a protection of a three-phase feeder. So here we have a three-phase feeder, bus A, uh, three-phase feeder, phase A, phase B, and phase C, and each of the phase is having we have two buses, bus A and bus B, and here we can see that bus B is connected with relay with a relay, and bus A is connected with another relay. And now you can see the arrangement of relay coils. So RA, RB, RC, for each phase there is one circuit, one CT, right? One current transformer for each of the phases. Similarly for relay B also, right? For relay A also, and for relay B also, right? And here we can see the circuit breaker arrangement. These are the trip contacts, right? And this is the trip coil, and here are the circuit. Here is the circuit breaker for both bus A and bus B, right? The circuit breaker gets the trip command from this as soon as the trip contacts are closed by the relays, right? And these are the IDMT relays. Okay, so when the current is flowing here IA in phase A, obviously the current flowing in the CT is IA by N, and also that current will flow by a phase A circuit, phase A coil, right? And that IA by N is nothing but the turns ratio, that is the CT ratio, right? N is to 1 is the CT ratio. Okay, so now for the different types of fault, how the relay will operate, we can see it here. So for different fault types, here it is given, and here the different relay operation is given for different phases, right? For fault type A to G, phase A to ground, the relay RA will operate, right? RA is here, RA, RB, RC. Similarly for B to G, RB will operate. For C to G, RC will operate, right? For AB fault, that is line to line fault, both RA and RB will operate. And for B to C, RB and RC will operate. For C to A, RC and RA will operate. Similarly, for fault A, B and G, your RA and RB will operate, not the other relays, right? So that will also trip the circuit breakers accordingly. Similarly, for fault BCG, RB and RC will operate, and for CAG, RCRA, and ABC, RA, RB, RC, ABCG, right? This is for three fault, ground fault, ABC, all the relay will operate. Okay, so this is how the relay arrangement is there for the three-phase feeder protection. Right, in detail it is given, right? Similarly, here we can see another type of arrangement, protection of three-phase feeder, where we are considering the ground fault. So we have obviously this relay we can see here, right? So here we can see phase fault over current relay RA RC, right? So for RA and RC, this will only one single coil will be sufficient for RC, and then for ground fault, there is a overcurrent relay here, that is RG, right? This is another type of arrangement for which for different type of fault the relay operation is shown. For A to ground fault, phase A to ground fault, relay A will operate, RA will operate, right? Here RA will operate, and for B to G fault, RG will operate. For C to G fault, RC will operate, because RC here, RC is here, right? RC will operate. And similarly, for because B to G, there is no relay at phase B. Here there is no relay in phase B, right? So therefore, your ground relay will operate for that. RG will operate. Similarly, for B to C, RG and RC will operate. For C to A, RC and RA will operate. And for ABG, RA and RG will operate. For BCG, RG and RC will operate. So there are different combinations for different types of fault, right? So what is the advantage of this kind of arrangement over the last arrangement? In the last arrangement, we can see here there is no ground relay, right? So this is in fact difficult to protect the earth fault. Okay, so therefore when and sometime it maloperates, right, for different faults. But here in case of in this kind of arrangement, it is more accurate, and when the ground fault is there, it is more accurately it will just detect the fault and give the trip command to circuit breaker. Okay, so directional overcurrent relay. So what is overcurrent relay and what is directional overcurrent relay? So overcurrent relay means it will if I'll put a relay here, okay, suppose I'll put a relay here, relay. So this will act in both the direction. When the fault happens at this point, then also it will act, and when the fault will happen in this direction, then only also this relay will operate. And certainly this kind of arrangement, or this kind of overcurrent relay, this has certain disadvantage for particular arrangement of network. We'll see it. So here an example is given. If the directional current would be here, suppose here it is a directional overcurrent relay, okay, directional overcurrent relay, then it will act only in one direction, right? Okay, so but if it is only overcurrent relay, so then it will act both the direction. So there are certain disadvantages of this. Let us see this. Okay, now we'll see here. This is one double end fade or double end fade distribution feeder, right? So this is a double end fade distribution feeder, right? So now how will it will protect when the fault is there? Let us consider the fault at location A, right? So what will happen? So considering this, let us say let us consider fault FA. Okay, here. So that is in the line 4-5, line section 4-5. Right, when this fault happens, what will happen? In fact, we need to isolate this fault. So circuit breaker 4 and 5 should operate. That means relay 4 and 5 should operate. Right. So direction of fault power flow at bus C. We'll see. Observe now. We'll observe the power flow at bus C as seen from 5, relay 5. When the relay will see the power flow from bus number C, how it will look. Okay. So for fault A, it will be away from bus C. If the relay 5 will see it, the power flow will be away from bus C. Okay, when for the fault FA, right? And similarly, the desired response of overcurrent relay at 5 will be trip, obviously, right? As I told. And the direction of the fault power flow at bus C, what will be the power flow when we'll see from relay 6? When we'll see from relay 6 for the fault FA, how the power flow will look like? It will be in this direction. That means towards the bus C. Okay, so it is towards bus C. Whereas when we look from relay 5 for this fault, for fault A, FA, it will be away from bus C. Whereas when we look the power flow from relay 6, it will be towards bus C, right? So then the here the desired response for the overcurrent relay at 6 will be to restrain, because it should restrain, in fact, right? Because it should not trip. But if it is overcurrent relay, it will trip even if the power is flowing towards bus number C. But the thumb rule says that if the power flow during the fault is away from bus, then it should trip, right? So, but it will also trip here. It will trip if it is overcurrent relay. If it is not a directional overcurrent relay, then this relay 6 will also trip, right? Even if the fault is here at FA. Similarly, if we'll consider the fault at FB, okay, at the section C and D, then how the power flow will look like at bus number C. At bus number C, when we'll look from uh, relay 5 for the fault FB, the power flow will be towards bus number C, and from towards bus number C. And when we'll see it from relay 6, when the fault is at FB, then it is away from bus number C. That means the desired operation for relay 6 is trip for FB when the power is flowing away from bus number C as seen by the relay 6. Under that condition, the desired operation of relay 6 is trip. Okay, and the desired operation of relay 5 for FB is restrain. When we'll see the power flow, it is towards bus number C for fault location FB, right? So that means what will be the thumb rule? The thumb rule will be, what will be the thumb rule? So from this we can conclude that for any kind of fault, if from the relay location, for any fault, okay, for any fault, if your power flow during fault as seen by the relay at a particular bus is away, then the desired operation is trip, right? Is to trip. Okay, so is to trip. But when we look from the relay for that particular fault, and if it is towards the bus, then the desired operation is restrain. Okay, so this is the thumb rule. Now considering the thumb rule, we can set the directional relay. So we'll see few more illustrations how the directional overcurrent relay is important. Okay, so here also we can see, though it is a single end feeder, but it has two parallel lines, right? This is a single end parallel line, right? Single fade, two parallel lines, right? So here also we need to have a directional relay. We can see here, right here, if the fault is here somewhere, if the fault is in this line 3, 4, now what will happen? Now we need to isolate 3 and 4, section 3 and 4, and if your relay 3 will look from the what will be the power flow from this bus? From this bus, the relay if will seen from the relay 3, it will be away from this bus, right? Let us mark this bus. Let us see. This is bus number A. This is bus number B. Okay. Now, if we'll see the power flow from relay 3 during the fault, it will be away from bus number 3, and it is really desirable operation for relay 3. That means it should trip. And if we'll see from the location of relay 4, the power flow from bus A, it is away from bus A, and it is also desirable, right? Okay. So if we'll come to bus, now we'll come to relay 2 for this fault, right? So for this particular fault for relay 2, if we'll see, the power flow will be towards bus, right? So that means this is not desirable. The operation of relay 2 is not desirable for this fault. That means we need a directional overcurrent relay for relay 2. So that means your relay 2 should be a directional overcurrent relay. Okay. Now if we'll see, similarly, if we'll make a fault here at this point, your relay 3 will find relay 3 will be your directional overcurrent relay, right? But for relay 1 and relay 4, it may not be directional overcurrent relay. Only overcurrent relay is fine for this, right? Okay. So therefore, because the source is here, the source is providing it, power, right? Source is providing the power, so therefore only R2 and R3 will choose the directional overcurrent relay here, because the tripping direction is only away from the bus. Okay. Similarly, here is another example of a mesh network. We call it a ring feeder, right? So it is a ring feeder. So similarly for ring feeder also we can find, now we can see here we have 4 buses, right? And in fact they are interconnected in a mesh form, and only source is E here, right? And that is providing all the buses, all the loads connected at different buses, right? Now the advantage of the ring feeder is that whenever a fault happens in any of the distribution line, then if it is isolated, then through alternate path the load is being fed by the source. Okay. So therefore it has certain advantage, and for this kind of network, in fact, we need the directional overcurrent relay, right? So here it has been shown for considering a definite time overcurrent relay. Okay, the arrangement has been done. We can see here from bus number bus number B, it was started, right? Then it was gradually going through in this way, right? Then we can see here bus number B, the time delay is set at 0.1 instantaneous, right? Then after adding 0.5 second, the backup relay for relay 2 is 4, right? So therefore the delay time or the TMS is set as 0.6. Okay. The delay time in fact set at 0.6 second. Then to relay 4, the backup relay will be relay 6, and hence the delay time is set at 0.6 plus 0.5, that is 1.1 second. And to relay 6, the backup relay is relay 8, so therefore your delay time is set at 1.6 second, right? So similarly it was found in clockwise direction, and similarly in anti-clockwise direction also it can be found, right? Okay, so from point 1 we'll start, right? So both way it is from here, point 1 is taken 0.1 second, then 0.6 second, right? 0.6 second, then 1.1 second. So clockwise started from relay 2, Okay, clockwise coordination started from relay number 2. Okay, that is 2. And anti-clockwise coordination clockwise coordination started from which bus, which relay? Started from relay 7. Okay, any relay you can consider, but in this figure from relay 2 and relay 7 it is started. We'll see in detail how to coordinate the inverse definite minimum time relay in the future classes. Okay, so let us see the characteristics of directional relay. So in fact, unlike the overcurrent relay, directional overcurrent relay has two coils. One is your current coil and other one is your pressure coil, or we call it voltage coil, right? But in case of overcurrent, normal overcurrent relay, only we have the current coil. It only takes the current from the CT, from the current transformer. And here we need both current and voltage, current from the CT and voltage from the VT or PT, right? Here we can see we have two coil, CC, that is the current coil, and other one is your potential coil. So current coil is fed from the CT, current is fed, and the voltage is fed from PT to the potential coil. Now we can draw the phasor diagram uh, for these arrangements for the voltage and current of the current coil and the pressure coil. Now we'll see, because we know when the current is under normal circumstances, generally the current in this network will lag the voltage in the network, right? If will this will write VPC, this is your ICC, right? But during fault it may lead or it may lag very hugely, right? Now let us say your current is leading here, that is ICC, right? ICC phasor is this, and VPC is taken as the reference phasor, and ICC is leading by theta. Theta is the angle by which your current in the current coil is leading the voltage in the pressure coil. Okay, so now uh, what will be the current in the pressure coil? So obviously it will be lagging because this is a inductive coil. So your current is lagging by the angle theta PC to VPC. Okay. So now we can see here uh, what will be the position of the maximum torque. That means, sorry, what will be the position of the ICC for producing the maximum torque? When the maximum torque will be produced? When the maximum torque will be produced? So from the torque equation, in fact, when this current ICC will be in the position of 90 degree with respect to phi IPC, that is, if the angle between IPC, that is the current through the pressure coil, the voltage coil, and ICC, the current through the current coil, is equal to 90 degree, then we'll get the maximum torque on the disk. So therefore, this line where the ICC is making an angle of 90 degree to the IPC, that position is called the position of ICC for maximum torque. Okay, so how it is, let us see. We know that operating torque is directly proportional to phi PC and phi CC. Phi PC into phi CC, sine of angle between these two fluxes, right? So angle between these two fluxes is So phi PC will be here in line with IPC, and phi CC is in line with ICC. So the angle between the phi CC and phi PC is this angle. That is nothing but theta plus theta PC. Okay, theta plus theta PC. So then I can write theta PC plus tau equal to 90 degree, right? So here theta PC plus tau, this angle is 90 degree. Okay, theta PC plus tau equal to 90 degree. From here I can find theta PC. So theta PC will be equal to 90 minus tau. So now substituting theta PC here in this equation, I will get T operating is directly proportional to phi PC, phi CC, sine of theta plus 90 minus tau. Now it will become phi PC, psi CC, cos of theta minus 9, theta minus tau, and that is equal to K1. I will multiply constant K1, phi PC, phi CC, cos of theta minus tau, right? So tau is nothing but the angle of, that is the angle between VPC and the position of ICC for maximum torque. So this angle is known as maximum torque angle. Okay, so maximum torque angle is represented as tau, right? So this is known as tau. So now I can write the T operating will be equal to your K2 VPC. VPC is on, obviously I can write VPC in terms of phi PC. So I can write VPC ICC cos of theta minus tau. So this is your T operating, right? Okay. Now from here in this, from here we can find the restraining region and trip region, trip zone and restraining zone, right? Okay. If your if your if your current lies somewhere here, current phasor, let us see somewhere it is lying here in this zone, then we can easily say that the torque developed is negative. Okay, so the torque developed for this case will be negative. So then obviously it will not work, and only for this region, wherever in any position in the trip region your ICC lies, then this will work. So that therefore it is known as the trip zone, and this is known as the restraining zone. So I'll explain it more in detail in the next class. Okay, so just this is how this is called the restraining zone and the trip zone. That means when the current phasor lies in this region, right, then we call it the trip zone, and when the current phasor lying in this zone, then we call it the restraining zone. That means opposing. So therefore when the current is flowing in the reverse direction, that at that time it will produce a negative torque, and this will directional relay will not work. Okay, so it will not respond to the a reverse current. Always it will respond to the forward direction current. Okay, so we'll talk about more about overcurrent relay in the next lecture. So thank you very much. We'll stop here. Thank you for your kind attention, and thanks a lot.